this point, we've covered a lot of the conceptual knowledge on electrostatics, and you've been given the tools and the equations. So now we need to create some scenarios and get some practice in applying these equations and concepts. So problem number 1 here shows a wall of charge or a slab of charge. And let's assume that it's been imbued with excess electrons, so that the wall is negatively charged. And also, we'll consider the case where we haven't really shown the full dimension of this wall. We'll imagine that it's very tall in comparison to this distance, r. In that case, we can assume that the electric field is very nearly uniform. I'll draw on some field lines. So remember, electric field lines are meant to show us what the force would be on a positively charged object, or what would the force be on a test charge. So like I say, if this slab has excess electrons on it, then any test charge released in the vicinity of this slab of charge would want to accelerate towards the wall. Okay, so then we know this charge here must be negative, because it looks like it's being forced opposite the direction of field lines. So this is an example of equilibrium. And the question here is, if we're given the angle and the length of the string and the mass and the strength of the electric field, can we solve for the amount of charge? Okay, so let's make a list here. Given L, theta, electric field strength, and mass, solve for Q. So make a free body diagram. There's some tension in the string. There's a force of gravity, mg. And then there's an electrostatic force. And this is the interaction of the charge with the electric field. So now, again, this brings up the question. We have to find force. And when we think about electrostatic force, we think of two equations. F equals QE, or F equals K Q1 Q2 over R squared. So take a moment and think about which one of these equations you're going to associate with this force vector. Have you made up your mind? Okay, so hopefully you agree with me that there's really no value in writing Coulomb's law. We can't identify any two discrete charged particles, but we can recognize that there's just going to be some value of electric field that we can think of as some constant numerical value. So we're just going to say there's a force here, F equals QE. So the same angle theta that describes the angle of the string can be shown here in our free body diagram. And that means we can break the tension vector into components. There's a vertical component to the tension. There's a horizontal component to the tension. And if this really does represent equilibrium, that means that T cosine theta, the vertical component, has to cancel with the downward force of gravity, and T sine theta, the horizontal component, has to cancel the electrostatic force QE. So if T sine theta equals QE and T cosine theta is equal to mg, you can get rid of one of the unknowns, right? Our list of given quantities didn't include tension, but we can cancel it out by dividing one equation by the other, and we'll have tangent theta is equal to QE over mg. And so if the question was just to solve for Q, all we have to do is multiply both sides of the equation by mg, divide both sides of the equation by E, and there we have it. The charge would be equal to mg tangent theta divided by E. Notice in this problem I didn't give any numerical values. I certainly could have. I could have told you that the mass of this object is 6 grams, or 6 times 10 to the negative third kilograms. And I could say that the length of the string is equal to 90 centimeters. And notice something interesting. That really didn't factor into our result at all anyway, right? And that makes sense because we're saying that the wall is so tall compared to the distance r, then even if the string was longer, there's no change in the strength of the electric field at this location compared to this location. Okay, so anyway, I'm not going to give values for the angle for the mass. Disregard that 6 grams, disregard the 90 centimeters. At that point, it's all trivial. Anybody can plug and chug numerically. Deriving this equation based on the free body diagram is the name of the game. Let's do another example problem. Here we have 3 charges, all of the same magnitude. Let's say each of these charges is equal to, how about 8 nanocoulombs. And they all sit at the vertices of an isosceles triangle. And that isosceles triangle we see is inscribed in a circle with a radius of 50 centimeters. So we have 2 questions in this case. A, what's the net electric field at the origin, at point O, indicated in this diagram? And our second question, what's the net force on this charge located on the y-axis? All right. So for the first question, let's show some electric field vectors, and we'll apply the superposition principle. So due to the charge I'm circling here, there would be an electric field vector pointing in this direction. Due to this charge, there's an electric field pointing in this direction. Now, these are the same magnitude electric field because the charges are equivalent and the distances are the same. In fact, I think you've already figured out the answer to this question. There are 3 electric field vectors, and we defined the net value, but because of the symmetry, we can tell that it's 0. So our answer to part A wasn't exactly trivial, but it sure was easy. If we have to find the net force here, again, we're going to have to apply the superposition principle. So let's draw some force vectors now instead of the electric field vectors. Okay, so there's going to be a force of repulsion between that charge and the charge in question. So let's draw in a force vector F. And likewise, there's another force vector pointing this way. Those are the same value, just because of the symmetry and the equal values of charge. So F is equal to what? K, Q, well, normally we say Q1 times Q2, but if they're the same, if this is 8 nanocoulombs, 8 nanocoulombs, and 8 nanocoulombs, then Q times Q just gives us Q squared over, I'm going to have to come up with a symbol here. So let's say the distance between these 2 charges is lowercase r. So capital R represents the radius of the circle, whereas lowercase r is any one of the 3 sides of our isosceles triangle. So this is going to be divided by r squared, which means this is the same amount of force, k q squared over r squared. All right. So we know the value of capital R. We aren't given the value of lowercase r. So let's see here. Well, it's getting a little messy, but just as this represents the radius, so does this. Let's draw this in here. We've got a isosceles triangle. Try to clean up our picture a little bit. Oh, that didn't come out so good, did it? Try again. Okay, there we go. And from one of our charges to the center of the circle is the same as the radius of the circle. Of course, I could do it from the center of the circle to this other charge. That's also the same value, r, 50 centimeters. And I think we agree that this angle right here would be 120 degrees. And let's see, this angle is 60, so that means this angle is 30. So is this one. So can't we use the law of sines at this point? We can say we're trying to find lowercase r. So the sine of 120 over lowercase r is the same thing as the sine of 30 divided by capital R. So the value we're looking for, r, is equal to capital R sine 120 over sine 30 if we do some cross multiplying. So that means the distance between any two charges is equal to 50 centimeters times sine of 120 over sine of 30, which means it comes out to, grab your calculators and verify for me, I believe 86.6 centimeters. Okay, so this problem is numerical. You can see I have a third problem waiting for you, but let's get that out of the way. Okay, so let's do some computation here. F all by itself is equal to 9 times 10 to the 9th Newton meter squared per Coulomb squared, multiplied by 8 times 10 to the negative 9th coulombs, quantity squared, all divided by 0.866 meters squared. Kq squared over r squared. So the meters get squared and cancel out, the coulombs get squared and cancel out, and we're left with newtons. Grab the calculator, see what you get. So we get a force of about 7.7 times 10 to the negative, I believe 10 to the negative 7th newtons. But we've got that force repeated here. Let's see. This whole angle is 60 degrees, so this whole angle is 60 degrees. I see what we have here. There's one force vector of 7.7 times 10 to the negative 7th newtons. Another force vector of the same magnitude, 7.7 times 10 to the negative 7th newtons. If we make an x and y axis, then we need to break both of these vectors into their components. So they each have horizontal components, but those are going to just cancel each other out by symmetry. So what we're really concerned with is the two vertical components to this force. And in each case, that would be F times the cosine of 30 degrees. But there's two of them, so our net force is equal to 2F cosine 30 degrees, and we can substitute 7.7 times 10 to the negative 7th for F. And so we get a final answer of about 1.33 times 10 to the negative 6th newtons. Last problem. We're given two charges, both located on the x-axis, and we have to find the location where we could put a third charge so that the net force is equal to 0. Okay, so we're told the charges are capital Q and lowercase q. And I'll tell you in this problem, as far as magnitude is concerned, the charge capital Q is greater in magnitude than the charge lowercase q. So where could we possibly put a third charge so its net force is 0? Well, a couple questions about that. One, is the third charge we're going to put in this diagram, positive or negative. Turns out it doesn't really matter. Wherever the net force would be equal to 0 can only be the location where the net electric field is equal to 0. And the electric field does not depend on either the sign or the magnitude of the charge. If we assume both these charges are positive, if I were to put a third charge right here, let's say I put a negative charge right here, it's going to be attracted to capital Q. It's also going to be attracted to lowercase q. However, its attraction to lowercase q won't be as great in magnitude as its attraction to capital Q because of the relationship in their magnitudes. So it certainly would not balance at that point. We could guess again. Make a bit of an educated guess here and say, okay, maybe it's right here. I put a negative charge. Then its attraction to lowercase q may well be just the same as its attraction towards capital Q. Would it be the same if this were a positive charge? I think so. Sure. If I put a positive charge at this location, then the vector I just drew here no longer represents the attraction to lowercase q. That represents the repulsion from capital Q. And then this second vector I drew is the repulsion from lowercase q. But those will be the same in magnitude as one another. So whether this is a positive or a negative charge at this point, that's the location where the net force would be equal to 0. And really that's because that's the location where the net electric field is equal to 0. However, this problem didn't state whether or not capital Q or lowercase q are positive or negative. So let's try to solve it in the case where capital Q is positive and lowercase q is also positive. Then our guess was correct, and we'll call this location right here x. In other words, we'll make a frame of reference where the y-axis passes through charge capital Q. In other words, capital Q is sitting right at the origin. Okay, so then back to this diagram we have two electric field vectors in opposite directions have to cancel one another out. So what we would have is k times, let's see, this electric field vector represents the repulsion from lowercase q. So this is k times lowercase q. Now, the distance between this point and lowercase q would be, it's not d, it's not x, it's actually d minus x, isn't it? Okay, so kq over d minus x quantity squared would have to be equal to, how do we calculate this vector? That's the repulsion from capital Q. So this is k capital Q over, that's just over x squared. Now the k shows up on both sides of the equation, so we can cancel that out. And by some rearranging, we get d minus x squared divided by x squared is equal to lowercase q over capital Q. And you might be tempted at this point to expand this, say it's d squared plus x squared minus 2dx. But I would advise against that. We can avoid having to use the quadratic formula as part of our solution if we go about it a simpler way. Probably the easier way is just take the square root of both sides of this equation. So now we have d minus x over x is equal to the square root of lowercase q over capital Q. Or d minus x is rad q over q times x. Let's see, let's add x to both sides of the equation. So d is equal to x times the quantity 1 plus rad q over q. So x is equal to d divided by 1 plus rad q over q. So in the case in which the two charges have the same sign, then the only place where the electric field could be equal to 0 is at a distance x found by this expression. What if it were the case where the charges are opposite sign? All right. So again, we'll put capital Q at the origin, lowercase q here. We'll say capital Q is positive and lowercase q is negative. Now, regardless of where I put my test charge, if I put it here, there's going to be a repulsion from capital Q and an attraction to lowercase q, and so those forces could never cancel one another out. That's true anywhere along the line connecting the two of them. So the net electric field cannot equal 0. Here I'll label region 1, region 2, and region 3. The net electric field cannot equal 0 in region number 2. So let's try region number 1. Well, there's going to be a repulsion from capital Q. There's going to be an attraction to lowercase q, but guaranteed this vector is going to be smaller in magnitude than the vector pointing to the left for two reasons. One, this charge is smaller magnitude, and two, the point in question is much farther away. So that's it. We figured it out. The electric field can't be 0 in region 1 or region 2, but it could be 0 in region 3. So let's show this again. There's going to be an electric field vector that represents the attraction between the test charge and this charge lowercase q due to the fact that lowercase q is negative. And there's going to be an electric field vector pointing to the right that would represent the repulsion between a test charge and our positive charge, capital Q. So this electric field vector is equal to k times lowercase q divided by, now we need to come up with some distances, right? We've already labeled this distance as d, and because we're trying to find some location measured away from the origin along the x-axis, certainly a good name for this is x. So this distance is x minus d. Okay, so that's it. This electric field vector is kq over x minus d, quantity squared, and the electric field vector that represents repulsion between a test charge and our charge capital Q would be k capital Q divided by x squared. So if we're setting these equal to one another, again, the k cancels out. Oh, and I know what you might be thinking right now. How come you didn't plug in negative q here? Well, I've already dealt with the fact that it's a negative charge by drawing this vector in some particular direction. At this point, what we're saying is the magnitudes of these electric fields are equal to one another. So I'm ignoring the sign of my charges and just considering the magnitude of my charges at this point. I wasn't ignoring the sign of the charges in deciding on the direction of these vectors. See, I didn't completely ignore the sign of the charge, but once I've considered that, I no longer have to include the negative sign. Otherwise, it would really be a double negative. I don't want to account for that negative sign twice. Q over x minus d squared is equal to capital Q over x squared. We cross multiply. X minus d squared over x squared is equal to lowercase q over capital Q. Almost the same thing we had before. The only thing that's changed is instead of d minus x, we have x minus d. We take the square root of both sides, and we have x minus d over x is rad ratio of charge, cross multiply, x minus d is equal to rad charge ratio x. If we rearrange and solve for d, we have d is equal to 1 minus rad q over q quantity times x, or better yet, x is equal to d divided by 1 minus rad Q over Q. Okay. Now perhaps you like some numbers on this one, so let's try again. This is a 9 microcoulomb charge. This is a positive. This is a positive 2 microcoulomb charge, and they're separated by a distance of 30 centimeters. How far away from the 9 microcoulomb charge is the location where the net electric field is equal to 0? So because in this case I said they're both the same sign, and we're going to use this equation right here. Let's copy that. So we get our answer by taking 30 centimeters divided by 1 plus the square root of 2 over 9. Now you might say I need to say 2 times 10 to the negative 6 over 9 times 10 to the negative 6, but that doesn't matter because it's in both those quantities. Okay? So what do we get? The square root of 2/9 is about 0.47. I add that to 1 to get 1.47, and I divide 30 by 1.47, and we get x is equal to very nearly 20.4 centimeters. If we change the problem and say in part B, we have the same magnitude of charge, positive 9 microcoulombs and negative 2 microcoulombs. Now where's the location where net electric field equals 0? Well, it can't be in region 1. It can't be in region 2. It has to be in region 3. We call this distance x, and now we're using this form of the equation. So we get 30 centimeters divided by 1 minus the ratio 2/9. So again, the square root of 2/9 is about 0.47. When subtracted from 1, we get about 0.53. And when we divide 30 by 0.53, we get about 56.8 centimeters. Okay, so figure not drawn to scale. If this represents 30 centimeters, then we don't quite have our figure drawn to scale, but we've got at least the right region here. So there you have it. A few examples of how we can apply these equations for electric field and electric force. Thanks for watching.